Hi, in this last recording, we're going to be looking at the Chapter 22 sample problems. Again, kind of like with the Chapter 21 sample problems, these equations are not on your reference table and therefore will either be given to you either by me or inside the Regents question itself, or you won't actually have to do them on the Regents. You'll have to know them conceptually rather than mathematically. Okay, so if you look at the first one, it says magnetic flux with a single loop of wire changed from 0.2 Webers to 0 in 0.4 seconds. Okay, what EMF is induced? So this is the induction. So when we cut through the magnetic field lines, we create a voltage or an EMF. Remember, EMF and voltage are the exact same thing. So what we know is we have a single loop, so N is equal to 1. We have our change in magnetic field strength, which is delta phi, is going, or change in magnetic field lines is delta phi, which is going to be 0.2 Webers. Okay, because we're going to go from 0.2 to 0, and we know the time is going to take 0.4 seconds. So the equation we're going to use here is the EMF, and I'll put that here. EMF, the script E, is equal to a negative N delta phi over delta T. Now, the negative is there to remind you that it's actually in the opposite direction, so actually I'm going to drop it right now because we'll use it and it'll be in you, it'll be what's given to you, but just know that it's going to be, the voltage is going to oppose the change that created it. So, we have 1 times 0.2 Webers divided by 0.4 seconds, and so we end up getting 0.5 volts. The unit for EMF is voltage, or volts. Next one says magnetic flux coil having 40 turns, so we know our N is equal to 40. And we know that our delta phi over delta T is 0.3 Webers per second. So it's going to change by 0.3 Webers, 0.3 lines per second. What's the EMF? So it's the exact same equation. E is equal to N delta phi over delta T. And so our N is equal to 40 turns. We multiply that by the 0.3 Webers per second. And so we end up getting 12 volts on that. All right, we look at the next one. This is our next one on the induction. So this is not giving us the change in lines cut, the number of lines cut per second. Instead, it's giving us the magnetic field strength and the length of wire. So in this equation, we'll show you here in a second. We have a wire, so a length of 0.4 meters. And you just cross magnetic field, and it has a magnetic field strength or induction of 2 times 10 to the negative second Teslas at a velocity equal to 5 meters per second. Now the equation you're going to use here is that E is equal to VBL. So the velocity of the line the wire cuts through, the size of the magnetic field strength times the length of the wire that's actually doing the cutting. So when we put that up, we get 5 meters per second times the length of 0.4 meters. Oops, I did that backwards. And magnetic field strength, which is 2 times 10 to the negative second Teslas, times the length, which is 0.4 meters. And so when we do that, we find we have an EMF of roughly 0.04 volts. Okay, the wire is a circuit having a resistance of 12. This should be ohms. I changed that in the next subsequent things. But it's resistance of 12 ohms, not watts. That's just silly. So we now know the EMF for the voltage, E, which is equal to V, which is equal to 0.04 volts. And we also know that we have a resistance of 0.2 ohms. I'm looking for current. So we're going to go old school here, and that I is equal to V over R. So I did the 0.04 volts. Put that in, divided by my resistance of 0.2 ohms, and I'm going to get 0.2 amps in that process. And lastly, they want to know what forces are required to go through. So here, we know that the current is 0.2 amps. We know the length of the wire is 0.4 meters, and we know the magnetic field strength is the 2 times 10 to the negative second Teslas. So we've got a force is equal to ILB, so Phil we're going to use here. So my 0.2 amps is the current that's flowing through the wire. My length is 0.4 meters. And my magnetic field strength, 2 times 10 to the negative second Teslas. And so when I put all that together, I get 0.0016 newtons, or 1.6 times 10 to the negative 19th. All right, the last two we're going to do with here have to do with transformers. Remember, transformers allow us, I got to pause this when we're loud. Okay, on these last two, we're going to be looking at transformers. And so with transformers, you know that you have the equation. Again, this equation will be given to you with the number of loops on the primary over over the number of loops on the secondary is exactly equal to the ratio of the primary voltage over the secondary voltage, and it's equal to the inverse ratio of the currents. And so we have an alternating EMF of 220 volts is applied to a step down. So we know our primary voltage. Okay, and that's going to be 220 volts. We have 1200 currents on our primary, so NP is going to be 1200 turns, and NS is going to equal 300. And they want to know what's the secondary EMF. So if I go NP over NS, and that's going to be equal to VP over VS. And so my NP, that's 1200. NS is going to be 300, and that's going to VP, which is 220 volts, and I'm trying to find my VS, and so my VS is going to end up equaling 55 volts. On our second one, we know our secondary current, so IS is equal to 8 amps. And we're going to use the exact same thing, so we're going to go NP over NS is equal now to IS over IP, and so we're going to go 1200 over 300, and that's going to equal 8 over IP. So when I solve for that, IP kicks out to be 2 amps. Okay. And our last one, transformers uses step-up EMF. Power input. Power input, P is equal to I times V. So since I went with the primary, I'm going to use primary current and primary voltage, so 2 amps times the 220 volts, so 440 watts is our primary power coming in. And our last one, what's the turn ratio? Well, the turn ratio, NP to NS. Yep. You are right now, they heard you. Is equal to VP over VS. And so I know that that's 110 volts over 55,000 volts. And so I'm going to reduce down to, thanks, Fed, 1 over 500. And that's our turn ratio. So I hope that helps and you enjoyed the entertainment. Have a great day. See you, bye.